Good morning, everyone. My name is Travis Walbeck here at NCAT. I'm the training manager and have some awesome opportunities to help out with things. And this is one that means a lot to me, is this implementation webinar that we've been doing. Welcome to the first one in the year 2023. Today, our discussion is going to be about the calibration of asphalt layer coefficient. There's been some exciting work done at NCAT that has saved some agencies, pretty decent amount of money because they're able to design their pavements a bit better that way. So today we're going to go along the schedule we normally do, with Buzz Powell's going to give us a background, and we're going to have Dr. Dave Tim also give us a discussion about what was done at NCAT. And then we have a special guest here, Kim Schofield, that is part of the Washington Asphalt Paving Association, and she's going to give us a perspective from when she worked at the DOT and some of the things that were done there in Washington. So with that, I want to ask that everyone stay muted as you can. Please put your questions into the chat box. We'll try to gather those up at the very end. We try really hard to end at the very top of the hour so we don't run into the rest of your day. So if you put those questions in there, some of the presenters will answer in the chat box, and we'll try to have as many of those we can discussed verbally at the end. Please remember that we're going to do this every month. The next one will be on February 16th. But given that, make sure we introduce our presenters here. So Buzz, he worked for the Alabama DOT for 12 years and then 2 years in the private sector where he had his own firm there. But he was part of the building of the first NCAT test track. He became the manager of that in 1999, and he's now an NCAT associate director and an Auburn University research professor. Dr. Dave Tim is the Brasfield and Gorey professor at the civil engineering department here at Auburn University. He also serves as an associate department chair. He's been at Auburn for the last 22 years, teaching and working on asphalt pavement structure design and analysis methods. Much of Dave's research takes place on the NCAT test track. He's a professional engineer in Alabama and an avid mountain biker. So I got to always add in something for him because he has so many hobbies. So Kim Schofield, she's a professional engineer in Washington and works for the Washington Asphalt Paving Association as their technical director. She has a bachelor's degree in engineering physics as well as a master's in civil engineering. Prior to joining the WAPA, she worked with the Washington State Department of Transportation for 28 years with experience in HMA mix designs, pavement design, pavement management, research, maintenance, and construction. She closed out her career with Washington State DOT as the state pavement engineer responsible for the designing and managing of the state-owned pavement network. So given that, I'm going to hand the time over to Buzz, and remember, stay muted and give us your questions in the chat box. Go ahead, Buzz.
Well, thanks, Travis, and good morning, everybody. Travis didn't mention a hobby for me because my hobby is the test track, right, Travis?
That's right.
Pretty much
right.
Everybody knows that. So
yes, we do.
Well, I appreciate the opportunity to be here as always, and provide a little bit of background on the topic for today, which, as Travis said, is recalibration of the asphalt layer coefficient for modern materials and methods. For those of y'all who have been with us in the past, we kind of always follow the same flow. I'll provide just a few minutes of background, and then our PI, in this case, our subject matter expert here is Dr. David Tim. And then on the practical side, Kim is going to talk about implementation in another jurisdiction, and then finally I'll come back and kind of pull everything together, hopefully with some practical takeaways for participants. And we always start out by saying, the science that we're going to talk about today is based on research, the NCAT side of things here that we've done at the NCAT pavement test track. And for those of you who might not know, this is a class of research that's referred to as accelerated pavement testing. There's two ways to do accelerated pavement testing. You can do it with load simulators that are typically super loaded and travel like 10 miles per hour at a relatively low speed. We do the other flavor of accelerated pavement testing here, where we use actual trucks, we use legal loads, we pull triple trailer trains so that we can do as many loads as possible per lap, and we run 5 trucks at a time, 2 shifts a day, 5 days a week. So the goal of our 3-year project cycles is to compress 10 million equivalent single axle loadings into about 2 years of fleet operations. And the track is broken up into 46 test sections where we study, we do research with mixing materials, we do research with pavement thickness, which is the topic for today. And then we also do research with pavement preservation. So to give you just a little bit of background, one slide here, and then I'm gonna hand over to Dave on on layer coefficient recalibration. The 2000 track was designed to be essentially perpetual using the 93 AASHTO design guide, which told us we needed about 2 feet of asphalt thickness in order to provide the performance that we really wanted to perform in that first research cycle. In 2003, and I think Dave came down with us in 2002-ish. But in the second research cycle, we ripped out some of the perpetual pavements on the north tangent, and we built what were essentially calibration sections for what we were calling MEPDG at the time. And these were 5-inch and 7-inch and 9-inch sections, which Dave is going to talk about in his presentation. In the 2006 research cycle, and we kind of reset our budget. The track is, you can kind of think of it as a nonprofit research business where we pay for construction on the front end and then do our fleet and research kind of on the back end. But we rebuild the facility every 3 years. And in 2006, we did some traffic extensions in some of those sections from the 03 track. We did some mill and inlay sections, and then we also added a couple of soft subgrade sections, a 10-inch section and a 14-inch section that I think Dave is going to include in his comments for today. In 2009, we did what we call the group experiment, where we did 50% wrap sections compared to virgin sections, warm mix asphalt, and a highly polymer modified binder. And essentially what we learned over the course of building all these test sections was that, although the track was designed to be perpetual using the 93 AASHTO design guide and the layer coefficients that were in play at the time, 9 inches of thickness we later learned provided perpetual performance. And then later, with innovative material like highly polymer modified binder, 5 3/4 inches provided what we believe to be perpetual pavement performance. So there's a lot of room for improvement and still be conservative with pavement thickness design. And Dave, I'm going to hand off to you there so that you can get into the weeds on the research that we've done with layer coefficients. And I got to figure out how to stop my share.
All right, thank you, Buzz. And
okay.
Hopefully, Buzz, can you hear me?
Yes, sir.
All right, very good. And I've got my slides up, so I think we're good here. I just got to rearrange a few other things. Good morning, everybody. Thank you for being here. We appreciate your time and attention this morning. And Buzz did a great job of setting me up for what I'll be talking about, which is recalibrating the asphalt layer coefficient, and specifically at the NCAT test track. And then I'll hand off to Kim to talk about similar but different work that was done in Washington State to achieve the same objective, which was to update how we go about designing asphalt pavements with the older 93 AASHTO design guide. Many states, I think currently over half of the U.S. State DOTs currently use the AASHTO 93 design guide, even though we have the new MEPDG and we have the AASHTOware pavement ME software and so on. Most states are continuing to use the old AASHTO 93 design guide for a number of reasons that I don't really have time to go into here, but it is still very prevalent, very commonly used. And even states that are using the newer design system oftentimes are also using the AASHTO 93. And as part of that, the structure coefficients, what we call these A sub I terms, these are key inputs. This is how we express the relative strength of the various layers. And I'm going to focus today on structure coefficient of asphalt, concrete, but it's how we express the relative strength of the base, sub-base, and so on, all the various materials that we might put into a flexible pavement structure. And it's really important because the structure coefficients are how we get to layer thicknesses. And so they're really critical to the design process. And most maybe alarming or most important about these structure coefficients is that many or most states use values that were set at least 30 years ago. Depends on the agency, but most of them set these at least 30 years ago. And when they set them, they were based on values that came out of the AASHTO road test in the 1950s. They were set in the early 1960s. So we're using really, really old structure coefficients to describe the relative strength of the materials. based on data that is at least 60 years old. And hopefully we would all agree that there's been at least a few improvements in how we specify and engineer our binders, our materials, and mix design and construction, all that kind of rolled together. When we use really old values from the 1960s, we're saying, well, forget about all that. We're just going to attribute the strength of the material to what was going on in the 1960s, as opposed to what we currently have in terms of our material design and engineering today. So just a quick review for those that are unfamiliar with how structural coefficients work in pavement design. If we think about a pavement structure, we have, for example, asphalt concrete over aggregate base, maybe an aggregate subbase over the subgrade. And based on whatever the materials are and say the modulus of the materials and other properties that we can characterize, we can quantify the structural coefficients, what we call this A1 for layer 1, structural coefficient layer 2 and 3. Then we also may have a drainage coefficient assigned to each of these the underlying base and subbase layers. And through the AASHTO 93 design process, we can compute the structural number that is required above each layer to protect it. So in a design like this, we would have SN1, SN2, and SN3, and we would design it in a top-down fashion to come up with what the layer thicknesses ought to be. So for example, SN1 is just the product of A1 of that material times the thickness of the material. SN2 is the sum of these two layers, and then SN3 is all three together. So once we figure out what the required SNs are, and I'll get to that in a second, we then just have to back solve for the thickness. So for example, this equation, if I know what SN is required to protect the base layer, I just take SN1 divided by A1, and that provides the required layer thickness. So these structural coefficients are just critically important to how we go about coming up with the thickness of all of the layers, and the focus today, of course, is of on the asphalt concrete. So where do those SNs come from? Where do each of these SN1, 2, and 3 come from? Well, they come from this medieval torture device, the so-called AASHTO structural design equation. And it's very complicated, and you can find nomographs like this to solve it in various textbooks and the AASHTO 93 design guide. It's very complicated. It's a big empirical equation, and I'll break it down a little bit and talk about how we go about solving it, or the importance of the various parameters. But basically, if we characterize 5 inputs, and that includes the traffic, the reliability and variability, the performance expectation, and the soil modulus, those 5 inputs, we can then solve the equation for SN, and that's how we get to that SN1, SN2, and SN3. One of the practical problems in using this equation is solving the equation for SN algebraically is nearly impossible. And so what we have are our nomographs like this, or we can program it into a spreadsheet and solve it numerically. But the point is, we put all this stuff into the equation. What pops out is the required structural number. And I think it's instructive to go back and look at or think about the AASHTO road test that was held in the 1950s. And these pictures were published in 1962. Before TRB was TRB, it was called the Highway Research Board. And these were published by them in the 1960s, just showing some of the things going on at the AASHTO road test. And what's really interesting is when you look at the data that came out of that road test, they had structural coefficients ranging from 0.33 up to 0.83. And these are average values representing that test loop and how many sections were in the loop and so on, and the corresponding R squared. But it's really interesting that the values range from 0.33 to 0.83. There was 2 loops that came out at 0.44, and AASHTO decided AASHTO at that time decided that they would recommend a 0.44. And as far as I can tell, and reading between the lines and so on, that is how we arrived at 0.44 virtually across the entire country. Was AASHTO said 0.44 is a representative number, and then it just migrated out to most every state. But the range of values was really from 0.33 up to 0.83. This map is a little bit out of date now from going back to 2014, but I don't think too many things have changed since then in terms of structural coefficients. And you'll notice the shading here that there's a lot of 0.44s in this plot. So anything that's yellow, orange, or I guess this kind of tan, light tan color or whatever, those are all 0.44. If you're in a red state, a red colored state here, that your state is using less than 0.44. And then there's two states, Alabama and Washington, and we're presenting about this today. Kim's going to talk about what's going on in Washington State, now use more than 0.44. And that may be the first time in history that Alabama and Washington State were ever mentioned in the same sentence about some engineering technology. So we're in the same boat here, that we're using above 0.44. And we're going to talk about how we got there and what the impact is on our pavement designs. Virtually the rest of the country, those that are using empirical design, are using 0.44 or below. So given the things that I've talked about already and the new advances that we've had in asphalt binder and mixture technology, and you know, if you think about the AASHTO road test, you go back to it, that was even pre-Marshall mix design. That was definitely pre-super pave. Marshall mix design didn't even exist yet. This was before we had SMAs and polymer modification, all the high-tech stuff and innovation that we find in the asphalt industry really didn't exist in the 1950s when those test sections were built. And so there's a need to update or recalibrate. We talk about updating, we're really talking about recalibrating the structural layer coefficient to reflect actual pavement performance. And this report we wrote back in 2014. You can find it on the NCAT website. I've got a link at the end of my slides that goes through procedures. There's a variety of procedures you can go through to recalibrate. And I'm going to talk about one of them using our test track data today. But this document, if you're interested in getting into a lot more detail, is freely available on the NCAT website. So the three different processes you can go through to recalibrate range from sort of relatively simple to relatively complex. And the first is using a deflection-based procedure. So you go out to an existing test section, you hit it with an FWD, you do some back calculation, and then you correlate the back calculated properties to structural coefficients using some old regression equations that again came out of the AASHTO road test. The problem with this approach is that it relies on those 1960s AASHTO correlations. So this is probably the fastest way to do it, but it's also this, and it's the simplest, but it also doesn't provide you kind of modern performance benefits in terms of the calibration process. The process that I'm going to talk about is performance-based procedures, and this is where you just recalibrate the structural coefficient to observed pavement performance. And this is really closest to what was done during the AASHTO road test. How they came up with those values, the 0.33 to the 0.88, those came out of the AASHTO road test by just calibrating the structural coefficients to observed performance. And so I'm going to focus on that, what we did at the test track. And then the more modern approach is to use mechanistic empirical based procedures. And this is what Kim will be talking about, what was done in Washington State. And basically it uses calibrated ME transfer functions. It is the most time and resource intensive, but if your area, your state is going through an ME implementation, at the same time that you're implementing it, you can go back and look at the existing performance of your pavement sections and calibrate using this more modern approach. And it is a good option if you've already calibrated the ME procedure, you have the data necessary to do this, or if you're in the process of doing it, you can recalibrate the structural coefficient very quickly. So Buzz has already talked about the test track. I'm not going to go into any more details other than to say that we really rely on this rapid application of traffic and weekly performance measurement to go through our calibration procedure. So the overall framework of how we recalibrated at the test track was, it all hinges on this idea that we have predicted traffic in terms of ESLs and then measured traffic. And in an uncalibrated mode, you might not have a good match between those. There might be a bias in the data. In fact, this is what we found at the test track, is that we were able to apply a lot more traffic than what AASHTO 93 would predict using our existing structural coefficients. So the idea is that you go through this calibration process and you take the bias out of the data and so on. Same thing we do with calibrating ME transfer functions, for example. So that begins with having actual traffic. So we know how many trucks and how heavy the axles are and so on, how many repetitions we have, and then actual performance. And this is characterized by weekly IRI measurement on the sections at the track. We can correlate that IRI through an equation like this to get to a serviceability index. That's that 0 to 5 scale that AASHTO likes. And from that, we can get a terminal serviceability and a change in serviceability, which are important to the AASHTO equation. And then what we're looking for is to come up with a new A1 that'll calibrate or take the bias and the error out of our data set. And we can use that to calculate a structural number. That can feed into that long equation that I showed earlier to give us the predicted traffic, the predicted log W18. And then I didn't show this equation, but there's another long equation that can be used to calculate how many ESLs based on all this other stuff over here. And that's where we get our measured traffic. And then it's a matter of adjusting A1 to get a good match between measured and predicted traffic. So we're just trying to calibrate that equation by adjusting the A1. So this is just to show you the sections that were used in our original calibration study. They span 2 different test cycles. And I'm not going to go into all of the details, but except to say they had mostly the same kind of pavement foundation, though we did have a couple of sections that we had an imported pavement foundation, a weaker subgrade, various aggregate base materials, various AC thicknesses, and then also various types of mixed designs and so on going on in this experiment. So it was a nice range, a nice sampling of asphalt materials that went into this, representing what we would call modern, although now it's 20 years old, these test sections or the materials that went into these test sections now 20 years old in some cases, but definitely a lot more modern than the 1950s. And what we did was converted the measured IRI to a PSI, serviceability index on the 0 to 5 scale. And this is just showing a couple of examples. In some cases, we did have a lot of pavement distress appear, and so the serviceability drops off. We choose some calibration points. In other cases, we really didn't have very much change in serviceability. And so this red line is the actual, but then to be conservative, what we did is we just sort of chose a value that was some reasonably low value. And rather than use the actual, we couldn't calibrate without a change in pavement performance. And so we chose that in some cases. And this is just showing some raw data. So if we use the 0.44 and we have predicted, measured the difference in the error, you can see using 0.44 for this example, we have a lot of error, very poor match. We have a lot more measured ESLs than applied. We go through the calibration process. We get a much better R² value. We get a much improved, still not perfect because of just random error. Still not perfect, but a much lower amount of error and a better structural coefficient to predict the actual pavement performance from our data sets. So this plot is showing layer coefficients for all these various test sections. And you notice they range from about 0.41 on the low up to about 0.68 on the high end within the range of the original AASHTO road test. And we just averaged these out and came up with a 0.54. And that's what we recommended to ALDOT. As a further evaluation justification for this, we also went back to the more simple method where we just run some FWD tests, back calculate, and come up with an estimate of the modulus. And some of you may be familiar with this correlation chart. This is in the AASHTO design guide, structural coefficient versus AC modulus. And if you look at all of our test sections and you just take this bottom equation here and put in 68 degrees, that's the AASHTO reference temperature, put that 68 degrees into this equation, what you get is an estimated modulus of about 800 something thousand. And quite miraculously, if you extend that curve, which came from the previous plot, if you extend that curve, extrapolate it out to what we have for our materials, what we come up with is a structural coefficient of 0.54, which as a researcher trying to establish credibility, I would have really loved to have this come out at 0.53 or 0.55 and not exactly 0.54. It looks a little bit suspicious, I know, but that's what we got. That's what we reported. So that was a good verification of what we got through the performance calibration. We did some additional validation work on a more recent test cycle. Buzz mentioned the 2009 cycle where we had some high wrap percentages, 50% wrap, hot and warm mix. We had a section with OGFC. We had some different types of warm mix on the track during this test cycle. We went through the same calibration process, totally new set of data, and what we came up with here was 0.55. Our recommendation to ALDOT was to not change the 54 that they had already adopted, that this was just another validation and verification of the earlier calibration, the first one that we did. So what does this mean in terms of pavement design? Well, the beauty of recommending a different and higher structural coefficient is that it's a % reduction. If you do the math on it, it works out to about an 18.5% reduction in pavement thickness. And so if it's a relatively thin pavement, well, there's not a lot of change there, but you get into some of these really high traffic situations, high ESIL numbers, and you may be shaving off, 2 or 3 inches from the pavement section. So it's a scaled thing where the thicker the pavement is, the more savings you realize. So from an implementation standpoint, and again, as a researcher, and at NCAT, what we're always striving to do is to have implementable results. And this is a really good example of very rapid implementation. So we finished the report in 2008. We provided it to our DOT. They reviewed it. They provided us feedback. And then in 2009, September of 2009, Federal Highways and ALDOT signed off on making the change from 0.44 to 0.54. So you see it here noted here and here. And so the way they implemented this was very straightforward. When you're using the Darwin software, using AASHTO 93, just change that asphalt structural coefficient to 0.44 to 0.54. The net result, we've been told by ALDOT, is about a $20 million a year savings by making this change. And the change has been in effect now since 2009. And they have not reported to us any ill effects or unintended consequences of making that change. They simply have calibrated the performance equation and the design equation to better reflect the performance they're getting out of their materials here locally. And so that has been a very positive change for us. It is a way to spread the paving dollar a lot further. So to just wrap up my portion here, so new advances in mixed design technology really warrants this. When I talk to folks about this, I encourage them to think about the types of materials they have and whether they should go through a calibration process. The structural coefficient has a big impact on the thickness design. We came up with 0.54. You'll hear Kim talk about arriving at a similar but not exactly the same value using a different approach. At every point, and I didn't talk much about this, at every point in our calibration process, we chose the conservative route in terms of kind of the worst case conditions. And so we think that this 0.54 is conservative. And really the impact here is this 18.5% reduction in thickness. That is a very significant impact for our state DOT in terms of dollars and how far they can make their tonnage go. Just a couple of references here. I think it's being recorded and Travis will make this available. But if you just go to the ncat.us, you can find these publications, recalibration. This is the report. And then how we recalibrated, and this is more of an overview of how you can go about recalibrating. And I hope I'm on time here, Travis, but that's all I've got. And I believe, Kim, I'll be handing off to you. I'll stop my share. All right.
Well, thanks, Dave. Awesome presentation and a great setup for mine, since I didn't do a lot of the background. So absolutely love that you were able to do that. One thing I'll mention before I get started is that, sorry, I don't want this display settings. Thank you. There we go. Sorry about that, guys.
That looks great, Kim.
it's always a little off on everything that we use. One thing that I wanted to say is that I just came from WashDOT, just started at our paving association here. So forgive me if I say we when I mean WashDOT. It's a little bit of habit after 28 years. And I was also there when we did this calibration effort. So I'll talk about our calibration effort. You'll notice from the dates that I have that we did ours pretty much directly after Dave and NCAT did their work. So we definitely learned from them, heard what they were doing, and we wanted to, you know, take a look and see what we could do here. So I'm going to get rid of this so it's not in my way. So we have a report out there as well, 2011, like I said, directly after NCAT did their work and Alabama DOT took over. I do have links in here if people are interested in it, but this is the work that we did. And it's basically, this presentation is just a summary of this report here. So what we did is we used the MEPDG. So it was the MEPDG back then. And we wanted to check what we were getting compared to the 93 AASHTO guide at all different ESA levels. So that's really what we did. Part of the effort that we went through for this calibration was to attempt to match the MEPDG outputs with our field performance. We've always had, dating back to the 60s, 50s and 60s, we've had some really smart people at the DOT design things that were perpetual, even though we didn't know what perpetual pavements really meant back then. So we had a lot of really good information and a really good field performance out of our pavements for many years. And then the other thing we wanted to do is we wanted to look at minimum layer thicknesses and the maximum lift thicknesses for our standard specifications. They were all incorporated into this so that we weren't having to, you know, make messes of, you know, what layers and the thicknesses that they should be and all that kind of stuff. So we kept that in the back of our mind when we were doing the rest of this stuff. Our pavement policy, the most recent is September 2018, but it is out there at the link that you see below. What you will see is basically a design catalog that is in our pavement policy, and that is what we reference our regions. We have 6 regions within the state. They design to the catalog first. If it doesn't quite fit, or if they have some specific data like different subgrade resilient modulus data or different drainage issues or different things like that, then we would go to the 93 guide. That's our backup to the catalog. Our backup might be the pavement ME, but we actually don't even have a license at this point in Washington. So we mainly use the design catalog that you'll see at the end of this presentation, and then we use AASHTO 93. Just want to touch a little bit on our pavement management system. It was a system that was made in-house many years ago, back in the 80s, basically. And it's morphed many times over the years, but it's got a lot of great, valuable information. And one of the biggest things is we have the construction history in our pavement management system from initial construction. No, it's not perfect, but it's really, really close. And we do still take cores to check and different things like that. But we do have a really good history of our pavements. So we wanted to take that historical data and the historical performance into account when we did this recalibration process. You can see, you know, this is just 2 tidbits of many, many, many things in our pavement management system, but this is basically the pavement thicknesses, and then you can see distress details down here, but we've got a ton of information in our pavement management system, and we wanted to take advantage of that. So what we did is we used, like I said, it was the MEPDG back then. The versions that we had already used and that we had available to us was version 0.6 for rigid, which I'm not going to talk much about, but I wanted to at least make that point here because these slides get used everywhere. And the flexible portion was version 1.0 in 2008. some of the design considerations that we design in Washington for 50 years. That's our design life for both types of pavement. It doesn't matter. We basically took our traffic levels and expressed them in easels because that was a little bit easier for the pavement designer to understand than traffic load spectra, but we actually converted it into load spectra. We took WIM data and all that kind of stuff. So we did what we needed to do, but basically we're expressing everything in easels when you see the charts. The base type that we typically use is a granular base, what we call a crushed surfacing base course. Except for our PCCP with higher easels, we wanted to stay away from that because we had some issues with it in the past. As I said, the thickness we based mainly on constructability and our minimum and maximum layer thicknesses and things like that. So we did a couple of assumptions so that we could get the right thicknesses for the pavement structure itself. Our subgrade soils, basically what our design catalog is based around is a resilient modulus of about 10,000 PSI. We found that that's pretty average and actually a little bit low on the conservative side for Washington State, except for in a few areas where we've got really some polluted soils and stuff like that. But overall, 10,000 is pretty conservative. If by chance, like I said, if somebody had some data where we're building brand new and we had a resilient modulus of 15,000, that is when they could actually use that data and design with the AASHTO 93 guide and use that number instead of the 10,000 in the catalog. So we do allow for changes. It's just that that's what the catalog is built off of. And, you know, Dave Tim walked through a lot of the variables that come into that big, long equation that he talked about, but the reliability levels that we used are 85% for easels of 10 million or less. And then we use 95% for the higher easels. Again, going on the side of conservativeness, you'd much rather have cracking from the top down instead of the bottom up, which I'll talk a little bit more about too in a few slides. And then we always do a double check for frost action. We have a state, it's very different from our west side to our east side. Our west side's more wet and moderate climate. Our east side can get a lot hotter and a lot cooler. So we do have frost action that we worry about. So we always do a double check for that, for the maximum depth of freeze. And we have some really good information in our pavement policy on some data back in the 50s, I believe, that we had a really hard freeze. So when we use the 93 guide, some of the specifics that Dave walked through, your serviceability indexes, we set to 1.5. We did a combined standard error for traffic of a 0.5. That's our standard that we've used forever. And we decided that that's one thing that we wanted to stick to. At the time, our layer coefficients for HMA were 0.44, and you'll see where we've changed that, and our gravel base was a 0.13. Typically for drainage, we design positive drainage design any way we can, just because we'd rather get the water out of a pavement structure. So we set it to 1.0 for all of our layers, and that's what our catalog is built on. But again, if we have something to where we can't design it that way, then we would look at a redesign with changing our drainage coefficients. So here's the pavement layer thicknesses from the 93 AASHTO guide with using a HMA layer coefficient of 0.44. You can see the reliability levels of 85 and 95% for the different levels of easels. And I threw in the concrete in here just because there's a fairly big difference between the higher easel numbers on the concrete and the HMA side when we were using these numbers. And one of the things that we were thinking about when we did this work was life cycle cost analysis as well, and what was reasonable for Washington State based on our data and historical performance that we had. So I throw that in, but I'm not going to talk about it. But you can see that they're saying that we needed, 14.5 inches of asphalt over 9 inches of base course for really high easel levels. And And we didn't really think that we needed that. So what we did is we went through the MEPDG, and like I said, we took the traffic with the WIM station data, load spectra, and all that kind of stuff. We did adjustments for the traffic volume. We looked at all the different vehicle class distributions, axle loads, AADTT, the truck traffic growth rates, all of that from historical data. So we took as much as we could from the data that we had, but we didn't have that specific test track data like NCAT had. So it was great to have something a little bit different, but yet following sort of the same thought process that NCAT had. Climate, we found that our default climate data from the weather stations in Washington was fairly accurate. So that's what we used. And then we actually went back to our design files, materials testing, standard specs, all that kind of stuff to look at our material and our structural properties to make sure that those made sense for those MEPDG inputs. So for HMA pavement conditions, the things that we used to figure out the pavement distresses was, like I said, a 50-year life total, but with proper rehab strategies. So we based that on our pavement design results and performance. Typically, we would get a pavement surface life anywhere from 12 to 16 years. Recall that I talked a little bit about Western Washington versus Eastern Washington. We do have a very big difference between those two in weather and different conditions with traffic as well. So we typically would get anywhere from 12 to 13 years on the east side, about 16 years on the west side. So we decided to just use 16 years for our surface life there. So that does come into play when we were talking about doing our MEPDG distress data. The terminal conditions that we used was IRI of 220 inches per mile, which might be a little bit higher than what you guys are used to seeing. FHWA, of course, uses the 170. We've always used the 220, and it's typically a trailing factor for us anyways. We usually trigger our distresses with cracking or rutting way before we get there with IRI. So we don't really worry about that, but we did use the 220. Longitudinal cracking of 1,000 feet per mile, fatigue cracking of 50%, transverse cracking of 1,000 feet per mile, and permanent deformation of 1/2 inch. So when we recalibrated the MEPDG, remember that I said that we used version 1.0 in 2008. We actually had to do a little bit of recalibration since then. And what we did is we compared the model outputs with our historical pavement performance based on that guide that was the recommended practice for local calibration. That was a guide from one of the NCHRP reports that came out when they were originally doing the MEPDG and how to go about that. So we actually followed that guide to get our model outputs. Our typical calibration sections, traffic levels, again, 50-year design ESOLs. We did use subgrade resilient moduli of 20,000, 10,000, and 5,000. That's typically what the spread that we see in Washington. 10,000 is conservative, but pretty typical across Washington state. Like I said, some of those Palouse soils that we'd see, we'd get down, around the 5,000 to 7,000 PSI range. And we do have some that approach 20,000 or more. Again, climate was Eastern Washington and Western Washington because we do have very different climates on both sides of the state. So our distress models that we use for the MEPDG, the alligator cracking model, the MEPDG back then assumed bottom-up fatigue cracking. As I said, WashDOT has a really good history of our pavements and our pavement performance. We have a history of some thicker pavements, and we see a lot of top-down cracking. And I actually have a link to the report in the notes of this slide, if you guys can see that when it gets published. But we did a fairly thorough study about top-down cracking. What we see is that any of our HMA pavements that are about 6 inches or thicker, we see top-down cracking and not bottom-up cracking, which really kind of goes to that whole over-design, issue. Are we over-designing with a 0.44 structural coefficient number? The MEPDG wasn't able to properly predict the type of cracking that we were seeing, but the rate of cracking was reasonable, is what we saw. The progression of cracking was questionable for the MEPDG. So what we saw is that it showed very different trends for different traffic loadings. So we weren't too confident in this model itself. The longitudinal and the transverse cracking models, we felt that they were fairly reasonable and they matched our historical conditions. When we go to the roughness and the rutting was calibrated for surface rutting only. Because we have those thicker pavements, we typically did not experience rutting in our base and subgrade layers. So we have a lot of pavements that, you know, are HMA 6 inches or thicker. And so we typically, when we see rutting, we usually can get rid of it with a mill and fill. And then the roughness model couldn't be calibrated because the default model underestimated our roughness. So we just didn't use that model, but it wasn't too big of a deal, as I talked about, because that's usually a trailing trigger for us. We typically trigger on cracking or rutting way before we touch our rutting or our roughness threshold. So basically the HMA pavement failures were defined by cracking and rutting only. And like I said, that matches our historical performance. So what we did is we compared it, and I just listed these again so you can see them in the same slide. We compared it to these conditions, and the 93 design guide were used as the input values. The MEPDG recalibration results came closer to our historical performance than the 93 AASHTO guide with an HMA coefficient of 0.44. So what we found is that we felt that the 93 AASHTO guide was producing overly thick pavement sections, especially for the higher ESA levels. But again, that was at the 0.44. So what we did is this is what we got out of the pavement layer thicknesses for the MEPDG. And you can see, and I have a chart in a little bit, that you'll have a comparison of the MEPDG versus the 93 guide, but you can see we were, I think it was about 1.5 inches thicker for the HMA at the highest ESA level. I think the pavement design guide was telling us 14.5 inches. So you can see that it backed it off a little bit, especially for those higher ESA levels. And that really did match what we were seeing historically. And we based a lot of our thought process on what were we seeing historically, because we didn't see a lot of pavement failures or a lot of quick pavement failures either. We had really good history and long life. So some of the discussion here, we did some adjustments to the revised structural design thicknesses. Like I said, HMA pavements averaged about 1.5 inches less than the 93 guide. For heavy traffic levels, HMA rutting predicted greater than 1/2 inch. So what we did there is we chose to use higher binder grades or potentially different types of mix, like an SMA or something like that, for higher ESA levels. So that's part of our design process. And then historical pavement performance played a huge factor in the final adjustments. Again, we designed to 50 years. I know a lot of states have lower design year lives, but we designed to 50. So we want to make sure it's perpetual, and that's what we're focused on. But we also thought that the 93 guide was being overly conservative. So our original pavement construction of our thick pavements, we didn't have structural failures. So here's the chart. So the first one under the layer thicknesses is with a coefficient of 0.44. Our adjustment was to a 0.5. We didn't go quite as high as NCAT and Alabama DOT at 0.54, though I think that there's definitely times that we could, especially if you're using a polymer modification or something like that. We do think that the 0.5 is still conservative, takes into account a lot of different assumptions that go into everything, but we feel very comfortable being able to change it from the 0.44 to the 0.5. I just threw this in here just because, like I said, we do adjust binder grades for issues that we may have with rutting. And then this is what is in our pavement design catalog. So right now, you can see, like I said, the PCC is in there, but life cycle cost analysis definitely went into our considerations with thinking about what works historically in Washington and what the MEPDG gave us, as well as what AASHTO 93 gave us. And that's all I have. So hopefully I didn't go too long either.
I think that was perfect, Kim. Let's see if I can.
Agreed. Kim, if you can unshare, that'll speed it up for Buzz.
Okay, I paused share. How can I unshare? Why do I not have that?
If you take the pause off.
I did. No, that's just my video. All I have is a new share, and I don't want a new share. Thank you. Sorry about that.
You're okay. Now I got to unshare. Got it. There you go, Buzz.
All right. Hey, as long as we get there, right?
That's right.
That's all that counts. That was a great job, Kim, and thanks, Dave. Can you see my takeaway screen, Travis?
Yes, sir.
Good deal. So, from our perspective, we've used the test track here to prove performance in structural test sections, in mill and inlay test sections, and in pavement preservation. And we like to say that we do research in 3 buckets: one in mix of materials, and then one in pavement thickness, and then one in preservation. And so it's all about really putting the best mix of materials in each layer, then knowing how thick the structure needs to be, and then maintaining the surface in the most cost-effective way through preservation when you have perpetual performance. And we have a lot of confidence in what we have done here at the track and what's been implemented from the track. I think, as I said in my introductory remarks, the 2000 through the 2009 tracks really are case studies in pavement thickness over design. In our case, with our subgrade and everything here, the 93 guide said we needed several feet of asphalt. We know that with conventional pavement, 9 inches was sufficient, and then we know with unconventional materials, 5 3/4 inches was sufficient. So that's really 15 inches of asphalt that we need to invest in other places. We touched on this just a little bit, but this is the 0.54 number is with conventional materials. So in 2009, we did a thinner pavement that was 5 3/4 inches using Hama binder, and this is not published information. I think this was mentioned in the chat box, but Dave and I did some quick calculations on this, and a conservative number to use with highly polymer modified binder was 0.77. And I say conservative because it never failed. So we assumed that at the end of 20 million equivalent single axle loadings, it would fail on the next lap, which is really kind of outrageously conservative. So that number 0.77 is way bigger than both 0.44 and 0.54. We think that the 0.54, based on everything we've seen, is still conservative for design. Kim mentioned their 0.50 they believed was still conservative. It's really, reassuring for us as researchers that we had that with the effort that was done in Washington that Kim described, that's an independent, completely off track corroboration with the research they've done, that the number needs to be significantly increased from 0.44. Not so that we can be a cowboy with our designs, but just that's the elimination of some of our excessive conservatism. And when you do that, and Dave mentioned this in his presentation, in Alabama, it saves tens of millions of dollars annually. And that money adds up. That's money that you can redirect to other needs on the network. And this increased number is applicable to both new construction, to lane additions, and then also mill and inlay rehabilitation. So that was all that I had here for the end in terms of takeaways. Travis usually takes over here for questions and answers. And if you want to do a screen grab there, that's all of our email addresses in case you would want to message us directly.
So a couple of questions that we have that have come in. I think you covered the one about the HIMA binder with that rough calculation of 0.77. But another question that came in is, have the studies looked at calibrating the different structural numbers for different mix types based on these levels? And so that sounds to me like that'd be a real granular level to say we're going to look at like an SMA versus a regular dense graded mix per ESEL type. So do you think there's been discussion of taking it that granular, Buzz?
There has been discussion of that, and we've kind of lumped, for most of the work we've done, we've lumped together our dense graded mixes. I'm not sure, is Dave still on the line, or did he have to jump off?
Went to class. Yeah, he went to class.
Okay, well, I don't want to jump his territory here, but we've lumped those mixes in together to do this calibration. So you would actually get a higher number for SMAs. But the one thing that we have studied is OGFC, and because most agencies that use OGFCs don't assign it any structural value, but we found, I think the number is 0.15 is the number that you could be using for OGFCs if you do use that for your buildups. So I think there is some value in doing research to separate out by mix type. I think the main takeaway from this webinar is that 0.54 should be conservative for both mix types, for SMAs and for dense graded mixes.
Yeah, that makes sense. So the next question that's come in is, has there been any work done on the different values for recycled mixes, FDR, CIR, CCPR? And I know the answer to that is absolutely. There's been some groundbreaking work done at NCAT. Buzz, can you cover that for a moment?
Yeah, and thanks for the plug there, Travis. And the number that we typically recommend for cold recycle mixes, whether it's cold in-place recycling or cold central plant recycling, is about a 0.35. So kind of in between an ag base and a hot mix layer, which is kind of what you would expect with cold recycle mix. Dave has published extensively on, and now Ben Bowers on the structural contribution of cold recycle mix, as well as cement-based FDR stabilization. And then we've got a lot of work that's ongoing up in Minnesota for the hard freeze, the wet hard freeze part of the country, where we'll be able to generate some even better data. What was the other part of the question, Travis?
I think that was it. It said FDR, CIR, CCPR. I think you've covered all of those.
Okay.
So that's the questions that we've seen come in there. I want to remind everybody that this is a monthly webinar series. We do it the third Thursday of every month. So our next one will be on February 16th here in 2023. We thought we had a topic picked, and then this morning we found out we didn't have the person we needed. So we're going to pick that on Monday. We'll push that out like we normally do. So please join us back again. We
always like to plug training in your pocket. So the slide that I'm showing right now is training in your pocket. Yep. And then there's the banner that ordinarily has a topic on it, but we'll work that out as we're going to develop the schedule for all of 2023 next week. So we'll be really happy to report on that in the future.
So, okay. Sounds good. Appreciate everybody joining. I appreciate Kim for you taking the time to join us as well early in the morning there in Washington. And
thank you guys.
Hope you guys all have a great day. Buzz?
Yeah, thanks everybody. Y'all all have a blessed day, and we'll look forward to seeing you next month.